Welcome to the Deep Dive. Today, we're really digging into something huge, humanity's, well, biggest ambition maybe. Not just popping over to the moon, but actually living there, building permanent bases, and maybe even using it as a stepping stone to Mars.
And you've provided some fantastic sources for this. They paint a picture that feels surprisingly close, much more practical than maybe people assume.
Exactly.
Yeah.
But there's this fundamental challenge, right? A huge hurdle. If we want to stay on the moon long term, it takes an absolutely incredible amount of energy.
And the environment up there, it's unbelievably harsh, just incredibly demanding.
Which brings us to the core of today's deep dive. The solution, which might sound a bit surprising.
Nuclear energy. It might seem counterintuitive, almost like science fiction, but it's rapidly emerging as the key, the linchpin, really, for making these lunar dreams a reality.
So that's our mission today. We're going to explore why nuclear power is so vital for the moon. We'll look at, how these systems actually work up there.
We'll dive into the specific technologies being developed, some really cutting-edge stuff.
The big advantages they offer, but also the very real challenges that still need tackling.
And the global collaborations making it happen, plus what it all means for, well, humanity's future out there in the solar system.
And importantly, everything we discuss comes straight from the sources you shared. So let's jump in. Let's start with the basics. Why is powering something on the moon so incredibly difficult? It's not like plugging in a kettle here on Earth, is it?
Not even close. The moon's environment presents unique energy problems. The biggest one, that day-night cycle.
Right, the long lunar night.
Exactly. You get a full 2 weeks, 14 Earth days of complete darkness every single lunar month. Just think about that.
2 weeks. So solar panels, which we rely on so much in space.
They're completely useless for half of the month. You just can't rely on them for continuous power.
Okay, so that immediately presents a massive energy storage problem if you were trying to use solar. Like unimaginably huge batteries.
Precisely, impractically large and heavy. And that's why solar, on its own, just doesn't cut it for a permanent base. But it's not just the darkness.
What else?
Well, the moon basically has no atmosphere, none to speak of.
Which means no wind for turbines, obviously.
Right. But maybe more critically, no air to help carry away waste heat from power systems. Cooling becomes a massive engineering challenge.
Okay, that makes sense. Heat dissipation in a vacuum.
And then there are the temperatures. During that 2-week night, it gets down to minus 280 degrees Fahrenheit. That's minus 173 Celsius. Just brutally cold.
Wow. Minus 280 F. So any power system has to survive that and operate through it.
Absolutely. It needs to function reliably through these wild temperature swings, from scorching sunlight to that deep, deep cold.
So for anything more than just a short visit, for actual sustained operations, you need something continuous, something dependable, independent of the sun, resilient to the cold. Which points back to nuclear.
It really does.
Okay, let's unpack the how then. When we hear nuclear reactor, most of us picture these huge facilities on Earth. How on Earth, or rather, how on the moon does that concept get adapted? How does it work safely in space?
Yeah, it sounds like a big leap, but the fundamental physics, the core principle, is the same. It's all about nuclear fission.
Okay.
So you take atoms of specific materials, uranium is common, we call them fissile materials, and you split them in a controlled way.
Controlled being the key word there.
Absolutely critical. It's a controlled chain reaction. It's not a bomb. It's a highly managed process designed for continuous energy release. And when these atoms split, they release a tremendous amount of heat.
A lot of heat, I imagine.
An enormous amount, yes. So you generate this heat safely within the reactor core. The next step is getting that heat out and turning it into electricity.
How does that part work?
You use a coolant. This isn't water like in many Earth reactors necessarily. It could be a liquid metal or a special kind of molten salt or even a gas in some designs. This coolant circulates through the hot core, picks up the heat, and then transfers it to a power conversion system. Now, that system might use the heat to boil water into steam, which then drives a turbine, sort of like a traditional power plant.
Okay, I see.
Or, in some more advanced designs, the hot coolant or gas might directly drive a gas turbine. Either way, you're converting that intense heat into mechanical motion and then into electricity.
Electricity to power the habitats, the science gear, everything.
Exactly. Life support, experiments, communications, maybe even rovers or resource processing equipment eventually. It's a self-contained power plant, miniaturized and ruggedized for the moon.
That miniaturization part sounds key. So we're not just shrinking Earth
Hmm.
reactors. These are new designs.
Oh, absolutely. This is where it gets really interesting. We're talking about innovative reactor types specifically conceived for the moon. One of the front runners is the molten salt reactor, or MSR.
Molten salt, how does that work?
Well, the really clever bit is that the nuclear fuel isn't solid rods, like in many reactors. It's actually dissolved into a molten salt mixture.
Dissolved, like sugar in tea.
Sort of, yes. And the salt mixture acts as both the fuel and the coolant circulating through the core.
Wow. What's the advantage of that?
Huge safety advantages. For one, these reactors operate at atmospheric pressure, not high pressure. That dramatically reduces the risk of, well, explosions or leaks.
Okay, lower pressure means inherently safer.
Right. And they have this amazing self-regulating property. If the
Mhm.
reactor starts to get too hot, the salt mixture naturally expands.
Uh-huh.
That expansion automatically slows down the nuclear reaction. It basically cools itself down, preventing a runaway situation or a meltdown. It's inherently stable.
That sounds incredibly robust, especially for a remote environment like the moon where you can't easily intervene.
Exactly. Then there's another really exciting avenue, thorium-based reactors.
Thorium, I've heard a bit about that.
Yeah, it uses thorium as its primary fuel instead of uranium. And the really exciting part for the moon is that thorium might actually be relatively abundant in the lunar regolith, the moon dust and soil.
Wait, so we could potentially mine the fuel on the moon itself?
That's the long-term vision. It's called in situ resource utilization, or ISRU. If we can eventually extract thorium there, it dramatically changes the game for sustainability.
Reduces the need to ship heavy fuel from Earth. That would be huge.
Absolutely enormous. Plus, thorium reactors tend to produce less long-lived radioactive waste compared to traditional uranium reactors, and they're inherently more resistant to being used for weapons, so environmental and security benefits too.
Okay, so MSRs for inherent safety, thorium for potential lunar fuel. And the others?
Well, there's also a focus on practicality and deployment. Rolls-Royce, for instance, is working with NASA on what they call microreactors.
Micro, like small.
Exactly, designed to be compact, relatively lightweight, under about 7 metric tons, and portable. The idea is you can land one, deploy it fairly quickly, and get power flowing.
How much power are we talking from something like that?
Their target is up to 1 megawatt of continuous power from one of these small units. That's a substantial amount, enough to power a significant early base.
Under 7 tons for a megawatt. That's impressive engineering. So we have these different, really clever approaches being developed.
Yes, tailored specifically for the challenges and opportunities of the moon.
So let's connect this back to the bigger picture. What does having this kind of reliable nuclear power actually enable on the moon? What does it mean for actually living and working there beyond just planting a flag?
It's transformative. It fundamentally changes what's possible. This isn't just about keeping the lights on or running a few experiments. It's the bedrock for, well, everything else.
Like what specifically?
Critical life support, running 247, 365 days a year, regardless of sunlight. Continuous scientific research experiments that might need to run uninterrupted for weeks or months.
Right, you can't just pause complex science for 2 weeks in darkness.
Exactly, and maybe the biggest one, large-scale resource extraction. If we want to get serious about ISRU mining water ice from shadowed craters, processing regolith for oxygen, or building materials that take serious, sustained power, nuclear provides that.
So it unlocks the moon's own resources, making a base more self-sufficient.
Precisely. And crucially, it provides that power through the 2-week lunar night. That eliminates the need for those gigantic, heavy, and frankly fragile battery systems you'd need with solar. A single nuclear reactor can power an entire base continuously for potentially decades.
Decades, with minimal maintenance.
That's the design goal. High
Yeah.
power density, lots of power from a small, long-lasting unit. Compare that to acres of solar panels that are vulnerable to dust, micrometeoroids, and those temperature swings, plus the massive battery farms.
Yeah, the contrast is stark. It really does feel like the difference between a temporary camp and a permanent settlement.
That's exactly it. It enabled persistence. It allows us to move from short expeditions to a true, sustained human presence off Earth.
Okay, it sounds incredibly promising, almost like the missing piece of the puzzle.
Right.
But nothing this ambitious is ever easy. Building a nuclear reactor on Earth is already a massive undertaking. What are the really big hurdles for doing it on the moon?
Oh, the challenges are immense, truly immense. First off, just getting it there, transportation logistics.
Right, launching something heavy and complex.
We're talking about multi-ton reactor components. You need advanced heavy-lift rockets like NASA's SLS or SpaceX's Starship. And then you need highly sophisticated lunar landing systems capable of setting down these heavy, sensitive payloads accurately and gently.
Gently being the operative word, I imagine. You don't want to drop your reactor.
Definitely not. It's not just about lifting power. It's about the precision and reliability of the entire delivery system, surviving launch vibrations, deceleration, the whole 9 yards.
Okay, so getting it there is challenge number one. What about operating it in that environment?
That's challenge number 2, the hostile environment itself. Designing reactors that function flawlessly in just 1/6 of Earth's gravity. That changes fluid dynamics, structural stresses, everything.
Hadn't thought about the low gravity aspect affecting the reactor itself.
And then there's the vacuum of space. Materials behave differently. Heat doesn't conduct or convect away easily. And those temperature swings we mentioned, from boiling hot in direct sun to minus 280 Fahrenheit in the shade or during the night, everything has to withstand that for years, decades even.
So incredible materials science and engineering are needed.
Absolutely cutting edge. And that brings us to probably the trickiest technical problem: thermal management, getting rid of waste heat.
Right. You mentioned no atmosphere to carry heat away.
Exactly. On Earth, power plants use cooling towers with air or large bodies of water. On the moon, you have none of that. All the waste heat generated by the reactor and the power conversion system has to be radiated away directly into space.
Radiated away.
With large radiator panels, you need highly efficient systems to collect the heat and then radiate it out as infrared energy. Designing these lightweight, deployable, and super efficient radiators that work reliably in a vacuum and don't get coated in dust. That's a major engineering feat in itself.
Wow, so transport, the environment, the cooling, it's definitely not trivial.
Not at all. It pushes the boundaries of engineering across multiple disciplines.
But despite these challenges, there seems to be real momentum. It's not just theoretical anymore.
Far from it. What's really encouraging is that this isn't just one country's dream project. It's becoming a truly global effort with some surprisingly ambitious timelines attached.
Global? Who's involved?
Well, you have major partnerships. NASA is working closely with Rolls-Royce, as we mentioned. That's a $50 million partnership specifically for these lunar microreactors. Their goal is a ground-based demonstration test by 2029.
2029 for a ground test. That's really soon.
It is ambitious. And they're not alone. You have the China-Russia initiative. They've announced plans for a joint lunar nuclear station, aiming for deployment somewhere between 2033 and 2035. Likely near the moon's south pole, where water ice might be accessible.
So parallel efforts from major space powers.
Yes, and beyond the big agencies, there's a whole ecosystem emerging. The sources mention a global research network, universities, private companies, spanning something like 12 different countries. They're all contributing R&D on things like radiation shielding, advanced materials, control systems. It's a broad front.
That's actually really cool to hear that level of international scientific collaboration on such a challenging goal.
It really is. It suggests a shared understanding that this capability is fundamental to the next era of space exploration.
So what does this ambitious timeline look like on paper, if things go, let's say, optimistically?
Well, the optimistic projections are pretty stunning. We could see ground-based prototypes being tested within the next couple of years, say 2026, 2027.
Okay.
Then maybe the first demonstration reactor launched not to the surface, but to lunar orbit for space testing around 2029.
Testing it in the actual space environment first. Makes sense.
Then the big step: deploying an initial, maybe smaller, 20-kilowatt reactor at NASA's planned Artemis Base Camp near the South Pole, perhaps by 2031.
Powering the first permanent U.S. outpost.
Exactly. And then scaling up. The really ambitious goal is a full-scale 1-megawatt reactor powering an expanded international lunar base, potentially operational by 2035.
2035, wow. That's just over a decade away. That feels incredibly fast.
It is incredibly fast. And if that happens, it sets the stage for the next leap. The 2040s could then see the start of ambitious Mars missions using nuclear-powered spacecraft, potentially refueled with propellant made on the moon itself using that nuclear power.
From lunar base power to Mars transport fuel. That's the trajectory.
That's the potential trajectory, yes. It's optimistic, requires sustained funding and overcoming those engineering hurdles, but it shows the sheer pace of development and the scale of ambition right now.
Okay, let's zoom out one last time. If we manage this, if we put operational nuclear reactors on the moon, what are the really profound, bigger picture implications? It feels like more than just lunar bases.
Oh, absolutely. It's foundational for our future as a spacefaring species. For starters, think about deep space exploration. Nuclear propulsion, not just power, enabled by these technologies could slash travel times.
How much faster are we talking?
Missions to the outer planets, Jupiter, Saturn, beyond, could potentially take weeks or months instead of many years. That completely changes the game for robotic exploration and eventually maybe even human missions out there.
Weeks instead of years. That just opens up the solar system in a way that's hard to fathom right now.
It really does. And then there's Mars. Sustainable colonies on Mars will almost certainly require robust nuclear power sources. The moon is the perfect place to test, refine, and prove these technologies before we commit them to Mars. It's a critical proving ground.
Learn how to do it reliably just 3 days away before trying it months away on Mars.
Exactly. And as we discussed, nuclear energy is the key enabler for making a lunar base truly self-sufficient. By powering that in situ resource utilization, turning lunar ice into rocket fuel, extracting oxygen from rock, it breaks the reliance on Earth.
Making the moon a genuine outpost, a stepping stone.
A self-reliant stepping stone. And importantly, the benefits might not stay in space. The sources highlight this too. The advanced materials developed for radiators, the ultra-compact and safe reactor designs, the novel waste management techniques. These could potentially spin off into terrestrial applications. Safer, smaller, more efficient nuclear power concepts, advanced materials. Innovations driven by the extreme demands of space could benefit us right back here on Earth.
That's a classic pattern with space exploration, isn't it?
Yeah.
Pushing the limits out there leads to breakthroughs back home.
It often does. It really puts into perspective that quote from Dr. Kathy Lueders at NASA. She said, "Nuclear power isn't just an option for lunar exploration, it's the key that unlocks humanity's permanent presence beyond Earth."
That really sums it up. It's not just engineering, it's philosophy almost. It's about committing to becoming a multiplanetary species. And this is the energy source that makes it feasible. Well, that brings us to the end of this deep dive. We've gone from the fundamental power challenges on the moon to these incredibly advanced reactor designs, the global race to deploy them, and what it all means for our future in space. It really is an amazing story unfolding.
It truly is, and it leaves you thinking, doesn't it? Considering how rapidly this technology is advancing for the moon, this aggressive timeline we talked about, and the huge implications, it makes you wonder.
Wonder what?
Well, what other energy challenges that seem completely impossible right now, maybe here on Earth, dealing with climate change, or maybe even further out in space, might actually be closer to a solution than we think, fueled, by the kind of intense innovation that this lunar ambition is driving?
That's a fantastic thought to end on. What other impossible problems might be unlocked by this push? Thank you so much for sharing the sources that allowed us to explore this. They were absolutely fascinating. And thank you, our listener, for joining us today. Keep exploring, keep asking questions, and we'll catch you on the next deep dive.